as we consider a broader variety of potentials when we solve the time-independent Schrödinger equation, we get a broader variety of solutions. The potentials that we're considering next have a couple of unique conceptual features that I'd like to talk about in a little more detail. Essentially, the difference between a bound state and a scattering state is the difference between the solutions to the free particle potential and the solutions for the, say, harmonic oscillator potential. We'll also talk a little bit about quantum tunneling, which is an interesting feature that can be used in a lot of ways in terms of practical applications, for instance, in quantum tunneling microscopy. But what we're going to talk about in this lecture is just a conceptual overview of these features. First off, let's consider what happens classically. If we have a potential, V of x, if you imagine having a little cart, for instance, rolling around on some sloped surface, this would then be the gravitational potential. And you know a cart in this position is going to be accelerating downwards, downhill, and it's going to roll around and roll back up until it reaches the height at which it started, until it reaches the same potential at which it started. To put this in a framework that makes a little more sense quantum mechanically, if I have some energy level, total energy level, for our cart, if it starts here with zero initial velocity, that level of its energy is essentially the total energy. Its potential energy at that point is its total energy. As the cart rolls downhill, it gains kinetic energy, having its maximum kinetic energy at the lowest point here. Then it rolls back up until it runs out of kinetic energy at the far point here. So we have effectively an allowed region here. The cart will never be found at higher potentials here or higher potentials here. So our allowed region covers the region between these 2 points, which are called turning points, since that's where the cart turns around. The space between the turning points depends, of course, on the energy level. If I had a cart, for instance, with an energy level here, either it could roll around on this side of the hump here, or it could roll around on this side of the hump. If it's on this side, you'll just have oscillations back and forth here. If it's on this side, you'll have oscillations back and forth here. If I continue to even lower energies, down here, my allowed region becomes smaller still, until I have just 2 turning points here, and the cart would just slowly wiggle back and forth between these 2 turning points. Classically speaking, it's not possible to have a particle with energy down here. This is not allowed. Essentially, the cart doesn't have enough energy at all to be on this surface. You'd have to lift the cart off the floor and place it in your bowl, for instance. This is for one particular type of potential, in particular one that goes up to infinity for large negative and large positive values of x. We can have other sorts of obstacle for our cart to roll over, for instance like a bump in the rug. If our cart comes in with enough kinetic energy to roll over this hill, we might say it has some energy up here, in which case the allowed region is, well, everywhere, all the way out to negative and positive infinity. If our cart doesn't have quite enough energy to clear the hump, then our allowed region is either just to the left of the hump or just to the right of the hump. A cart that does not have enough kinetic energy to clear this hill will roll up the hill, stop, and then turn back. A cart rolling in from the other direction would roll up the hill, stop, and turn back. So that's what we would expect a classical object like a cart rolling around on a surface, for instance, to make an analogy between this potential energy V of x and the gravitational potential energy. That's what the behavior of such a cart would look like. Quantum mechanically, we have a different picture. You know what happened in the quantum harmonic oscillator when we talked about a particular energy level. Consider an energy level here. The general behavior of the wave function psi depended on whether we had a potential energy that was higher than the energy that we were working with or lower than the energy that we were working with. So for instance, if I say the energy of the separation constant E in the derivation of the time-independent Schrodinger equation, the energy of the stationary state, if the energy is greater than the potential at a given point, then our psi curves towards the axis. We get sort of wave-like behavior for psi if the energy is greater than the potential. Now, if you remember what happened if the energy was less than the potential, we got wave functions that curved away from the axis. And that generally posed a problem for our normalization unless we were sort of pointed towards the axis the right amount, such that curvature away from the axis led to the wave function just coming and kissing the axis and then never leaving again. This is just from consideration of the behavior of the time-independent Schrodinger equation at a particular energy. If you think about, for instance, a constant potential. Energy above the potential leads to curving towards the axis, sort of wave-like behavior, whereas energy less than the potential leads to curvature away from the axis. Either wave functions that go on to join the axis or wave functions that curve away from the axis and cause problems for normalization. So in the case of this arbitrary potential now, what our wave function might look like, I'll plot psi in green here. In regions where the potential is larger than the energy, we know we have to have this sort of coming towards the axis to kiss the axis sort of behavior, something like that. We have to have that on both sides. Otherwise we'll have a wave function that's not normalizable. In between, we have to have some sort of wave behavior. Since the energy now is above the potential and we're going to have curvature towards the axis. Now I haven't tried to make this a rigorous sort of solution, but this is what your wave function might look like. What that means is that the allowed region, the region where we'll find the particle, is the region where we have some wave function that is, non-zero. And we have wave function that's non-zero, even beyond the classical turning points. So our classical allowed region would be in between these two turning points. But our quantum allowed region is going to continue out past. And it's not going to have particularly sharp boundaries here. This would be our quantum allowed region, going all the way out, even beyond the classical turning points. So this is a little bit different. Another scenario in which we have this region extending beyond what would be considered allowed classically is if we have an energy level, say, in this region. If our energy of our stationary state falls in this region, our quantum allowed region is again going to extend beyond the classical turning points here. It's going to even span across this small region here. So in spite of the fact that our overall energy is lower than the potential here, we still have some probability of finding the particle there. This is different than our classical behavior. One comforting fact is that the energy, a quantum particle having a stationary state energy below the potential everywhere is still not allowed. And you can understand what might happen with that, because everywhere having an energy below the potential means that everywhere you have the wave function curving away from the axis. So if the wave function is, say, coming down to kiss the axis here, because we know we need something normalizable, it's just going to keep curving away from the axis here, and we'll get something that is completely non-normalizable. Same thing happens if I try to make it kiss the axis on this side. I'll get something that blows up in the positive direction. So we're still not allowed to have energies below, but for limited regions. Here the energy of the wave function is below the potential, but this is a finite region. So we can have this sort of coming down to kiss the axis behavior. Same thing sort of holds for this region, except we don't have to have the wave function come down to completely reach the axis here. We could have a solution that looks something like this, for instance. If our wave function is, curving towards the axis here, then coming down, instead of to kiss the axis, just curving away from the axis, but then now the potential being smaller than the energy level again means we're curving towards the axis. And I need to draw this slightly better. Curving towards the axis until here, when again the potential is higher, and then we have to come down to kiss the axis because we're running out of space. You can have the same sort of thing happen on this side, curving towards the axis since our potential is smaller than our energy, and then over here coming down and over to kiss the axis. So our wave function never really came to kiss the axis in this central region. We never quite ran out of amplitude of our wave function, if you want to think about it that way, in our curving away from the wave function, but we didn't have any problems with normalization either. These regions where the potential is larger than the energy can still have, in principle, some probability of finding the particle there. For the case of our hill potential, we can still have quantum mechanical states that have energies higher than the peak energy in the hill. And for those states, our quantum allowed region is going to be all space. For quantum mechanical states with energy below the highest peak of the hill, we can again have this sort of behavior where we have a quantum, I forgot to turn off my ruler, quantum allowed region on either side, and spanning all the way through. We have a quantum allowed region everywhere. And we'll find out what wave functions look like that satisfy this sort of potential later on. We know we're going to have wave-like behavior here, wave-like behavior here. In the middle here we're going to have wave function curving away from the axis. So just to try and draw something, we might have something that looks like this. Let me try again here. Wave function that looks like this. Now in this region where the potential is higher than the energy, we curve away from the axis, and then start curving back towards the axis again on the other side. So our wave function might look like this, but it's going to extend to both positive and negative infinity. This sort of, the solution to the time-independent Schrodinger equation at regions away from our hill looks like our free particle solution. Since we have a constant potential, we might as well set that constant potential equal to 0. So essentially what we've got here is free particles on one side, free particles on the other side, connected by some region where it doesn't look as much like a free particle, but it still has some probability of finding the particle there. If you had, for instance, a traveling wave coming in from the left here, you would have a traveling wave going out to the right on the other side. So your particle, which has not enough energy to clear the hill, still somehow makes it through. This is called tunneling. And the probability of a particle passing through a barrier that's essentially impossible for a classically equivalent particle to cross is the phenomena of quantum tunneling. If you imagine what would happen classically, your cart coming in here is going to roll up the hill, stop, and turn back. It will never, ever magically pass over the hill. The absurd analogy that people like to use for this is imagine walking through a door without bothering to open it. There's some energy necessary to pass through the door, and in the case of something like a human being passing through a door, that energy would be very, very large. But it is in theory possible for you to pass through the door without interacting with it. It just has a very, very small probability of happening. If this barrier were extraordinarily large, you would have enough curvature away from the axis that it would be very difficult to normalize your wave function unless it came down and kissed the axis. And that's what we're working with in classical physics. But just briefly to summarize those two terms, or those two sorts of states, for potentials that looked like something like this, like the harmonic oscillator potential, we have energy levels that result in states that cannot exist in certain regions. So we have confined states, confined wave functions. This is what we mean by saying something is a bound state, that the wave function is confined. Since the wave function is confined, it's normalizable, and the exact number of waves, for instance, that fit in the region that would be classically allowed in the quantum mechanical case is usually quantized by the boundary conditions. Scattering states, on the other hand, if we have a potential that looks, say something like this, where we have energy levels that are above the lowest, those wave functions will extend to infinity because there's no reason that you can't find the particle here. As a consequence, they're non-normalizable. And since we don't have any boundary conditions that are requiring something very specific about the value of the wave function as it comes down to kiss the axis in this case, or In the case of a free particle, we don't have that. We can have the wave function do whatever the heck it wants as it goes out to infinity. We don't have a quantized spectrum. We don't have any boundary conditions to induce quantization. So you end up with a continuous distribution of energies. There's nothing to prevent energies of basically any value in this region. It's even possible to have potentials that have both. For instance, if I had an energy level down here, I could have wave-like behavior here, and then coming down to kiss the axis on either side. This sort of looks like a quantum harmonic oscillator state. This sort of looks like a free particle state. So it's possible to have both for the same potential. The other process that I mentioned, quantum tunneling, happens for potentials that look like a barrier, where the particle classically would not be able to pass through the barrier because it doesn't have enough energy. But quantum mechanically, the allowed region includes even the barrier and extends on both sides of the barrier. So that's bound states, scattering states, and tunneling. To check your understanding, consider the potential shown in orange here, V of x, and describe the states that exist at particular energy levels, whether they're free or bound, for instance, where you would be likely to find the particle if you were to observe it at a particular energy level, for example. Second question, does this potential have bound state solutions? And third question, does this potential have scattering solutions? Not bound scattering solutions. Ignore that word. Scattering state solutions. Part of this position is going to be accelerating downwards, downhill. And it's going to roll around and roll back up until it reaches the height at which it started, until it reaches the same potential at which it started. To put this in a framework that makes a little more sense quantum mechanically, if I have some energy level, total energy level, for our cart, if it starts here with zero initial velocity, that level of its energy is essentially the total energy. Its potential energy at that point is its total energy as the turns around. The space between the turning points depends, of course, on the energy level. If I had a cart, for instance, with an energy level here, either it could roll around on this side of the hump here, or it could roll around on this side of the hump. If it's on this side, you'll just have oscillations back and forth here. If it's on this side, you'll have oscillations back and forth here. If I continue to, which is an interesting feature that can be used in a lot of ways in terms of practical applications, for instance, in quantum tunneling microscopy. But what we're going to talk about in this lecture is just a conceptual overview of these features. First off, let's consider what happens classically. If we have a potential, V of x, if you imagine having a little cart, for instance, rolling around on some sloped surface, this would then be the gravitational potential. And you know a cart rolls downhill, it gains kinetic energy, having its maximum kinetic energy at the lowest point here. Then it rolls back up until it runs out of kinetic energy at the far point here. So we have effectively an allowed region here. The cart will never be found at higher potentials here or higher potentials here. So our allowed region covers the region between these 2 points, which are called turning points, since that's where the cart. As we consider a broader variety of potentials when we solve the time-independent Schrödinger equation, we get a broader variety of solutions. The potentials that we're considering next have a couple of unique conceptual features that I'd like to talk about in a little more detail. Essentially, the difference between a bound state and a scattering state is the difference between the solutions to the free particle potential and the solutions for the, say, harmonic oscillator potential. We'll also talk a little bit about quantum tunneling,